you hear me and see the board okay at home? Yeah, okay, here we go. So guys, yesterday you finally saw and hopefully understand now what the unit circle represents, right? Basically, in a nutshell, the unit circle is centered at 0, 0, and it has a radius of 1. 1 unit, which is why it's the unit circle. The radius of 1 is the easiest radius we could possibly work with. It has 17 angles and 17 ordered pairs. Technically, you could argue it's only 16, but I just count 0 and 2 pi as 2 separate angles, so I count this ordered pair twice. Otherwise, it's 16 and 16, okay? We learned yesterday that each point on the unit circle has an extremely important meaning. We learned that the x-coordinate of every single ordered pair on this unit circle represents the what of that angle? It represents, anybody remember? The x-coordinate represents the, starts with a C, the cosine. It represents the cosine of that angle. So if I ever asked you in the future, hey guys, what's the cosine of 5 pi over 4? You'd go to 5 pi over 4, the x-coordinate is negative root 2 over 2. So if you have this circle handy and available, it has every answer to all of these special trig ratios that we're ever going to ask you. So it is a great tool. If you don't have it though, then you kind of have to know how to create it or at least find these ratios yourself. All right, we learned that the y-coordinate of every single ordered pair represents the what of each angle? The sine, right? If x is the cosine, then the y-coordinate is the sine. And I just remember it because it's alphabetical. X, Y, C, S. So x cosine, y sine. And then the tangent is not visible. The tangent of an angle is not visible on the unit circle. However, we learned that tangent by definition is the sine over the cosine. So by definition, it's a y-coordinate over an x-coordinate. So you can always build a tangent ratio by saying, hey, what's the tangent of 5 pi over 3? Go to 5 pi over 3. The tangent is the y-coordinate over the x-coordinate. And you could build the tangent ratio just by putting the y over the x. Okay. Then I showed you yesterday, which you're kind of like, still not really sure why she told us all this, but you'll see when we start doing the problems tomorrow. If the x and the y coordinate represent your sines and cosines, so the ordered pair in quadrant 1 is xy. The ordered pair in quadrant 2 is negative xy. The ordered pair in quadrant 3 is negative x, negative y. The ordered pair in quadrant 4 is x, negative y. So that means the cosine of any angle in quadrant 1 will be represented by a positive x-coordinate. So the ratio is always positive for an angle in quadrant 1. The y-coordinate represents the sine of all that angle. So any angle that lands in quadrant 1 will have a positive y-coordinate. It'll have a positive sine ratio. So the sine of any angle that lands in quadrant 1 will be positive. All right, the cosine of an angle in quadrant 2 is a negative ratio. The sine of an angle in quadrant 2 is a positive ratio. The cosine of an angle in quadrant 3 is a negative ratio. The sine of an angle in quadrant 3 is a negative ratio. The cosine of an angle in quadrant 4 is a positive ratio. The sine of an angle in quadrant 4 is a negative ratio. So we have all students take calculus to help us remember which quadrants produce a positive ratio for this trig function and which quadrants produce a negative ratio for each trig function. All right, so all trig functions have a positive ratio for angles in quadrant 1. Only the sine ratio is positive for angles in quadrant 2. Now, this includes their reciprocals, so it would be sine and cosecant. Go ahead.
This sounds like it's going to be fun.
Nothing is.
Is that a P or a plus X?
It's a plus. I just put all positive, sine positive, tangent positive, and cosine positive. All right, only the tangent of an angle in quadrant 3 will be a positive ratio because it'll be a negative y over a negative x, which is a positive ratio. And then if you are an angle that lands in quadrant 4, only the cosine of that angle will produce a positive ratio. All the other trig functions have a negative ratio. So like I said yesterday, each trig function has a positive ratio in 2 quadrants and a negative ratio in 2 quadrants. Sine is positive in 1 and 2, but it's negative in 3 and 4. Cosine is positive in 1 and 4, but it's negative in 2 and 3. Tangent has a positive ratio in 1 and 3, but it has a negative ratio for angles in quadrants 2 and 4. So that comes in handy if you're not going to rely on the unit circle. Because guys, in the future, when we're hopefully not in virtual school and you're in calculus and maybe you don't have a unit circle at your disposal that you're able to have in front of you, then you kind of have to know these values without the unit circle. And that can help remember, should my ratio be positive or negative if my angle's in quadrant 3? It can help you remember your signs, okay? All right. I want to show you today just how the unit circle actually came to be constructed. So if you ever wanted to reconstruct it on your own from scratch, you could. And there's also an extremely short shortcut to that I'll show you afterwards. All right, but here we go. So before we construct the unit circle, we have to work with our special right triangles because these are our special angles that we put on the unit circle. Our 30s, our 60s, our 45s, and the multiples of them. I don't think I can fit that with it. I'll have to leave it here. All right, so guys, here we go. Let's make our special right triangles, because if you can create this triangle from scratch too, you should never need the unit circle. You shouldn't need it. All right, so let's take an equilateral triangle. So we have all angles equal, and all sides are equal, and let's bet it be 2 to make it easy. All right, if you drop in altitude straight down, because this is an equilateral triangle, this altitude is actually an angle bisector. So it cut this angle in half into 2 equal angles, and it cuts this side of the triangle in half as well. It bisects this side. So if the whole side was 2, now we have 1 and 1. So I'm just going to take this left triangle out over here. So we have a 60, a 30, a 90. I now have this side is 1, and my hypotenuse is still 2. So now using Pythagorean theorem, a squared plus b squared equals c squared, I can find the length of that altitude. So 4 take away 1 is 3, square root it, and you find root 3. I think in geometry, they hit you guys pretty hard with this relationship where you always know it's 1 to root 3x to 2x and all that. You should remember that, all right? I always remember it like this. It's 1, 2, and root 3. The littlest angle should have the littlest side across from it. So the 30 gets the 1, the 60 gets the root 3, because that's like 1.73, and then the 90 gets the 2. The biggest angle gets the biggest side, and the littlest angle gets the littlest side, all right? All right, so guys, if you can draw this triangle from scratch, you're always going to know what the sine, cosine, and tangent of a 30, 60 is. So let's fill in our chart. Guys, pi over 6 is 30 degrees. What's the sine of a 30-degree angle? Sine 30 would be O over H. It's 1/2. Guys, I don't know what it is about that, but my pre-calc teacher drilled into our heads that the sine 30 is 1/2, sine 30 1/2, sine 30 1/2. I want you guys to be 90 years old telling your great-grandkids, hey, do you know the sine of a 30-degree angle is 1/2? Like, I want you to remember it. I will say this so much to you that I kid you not. Every single card I have received from a student, and it ain't much, they put this, they signed it with sine 30 equals 1/2. I had a kid email me from college. He's like, hey, he's a cross-country runner at Stockton. I was on a run today, and I literally just thought, sine 30 is 1/2. In the middle of his run, he said. So please, if you can remember that, everything else will fall into place. All right, sine 30 equals 1/2. What is the cosine of a 30-degree angle? Cosine is root 3 over 2. And then tangent, what is the tangent of a 30-degree angle? Tangent would be O over A, which is 1 over root 3. But when you rationalize it, you get root 3 over 3. And the way I remember that is the tangent of a 30, he's got a lot of 3s. 30, a lot of 3s. All right. Now if we work off the 60, because you have to know the sine, cosine, and tangent of a 60 off the top of your head, the sine of a 60, which is pi over 3, what's the sine of a 60? The sine of a 60 is root 3 over 2. So I always remember it, if the sine of a 30 is 1/2, then the sine of a 60 can't be 1/2. It's got to be that other ratio, root 3 over 2. All right, what's the cosine of a 60? The cosine of a 60 is 1/2. And the same thing, if the sine of a 30 is 1/2, the cosine of a 30 can't be 1/2, but the cosine of a 60, his complement, is 1/2. All right, and then the tangent of a 60, tangent 60 would be √3/1, so √3. So not so many 3's. All right, now guys, if you notice, 30s and 60s, sines and cosines. Guys, look at these ratios. 1/2 √3/2. 1/2 √3/2. Let me see if I can do this. Look at your unit circle. Look at all your sines and cosines. Look at all your x and y coordinates. They're 1/2. They're √3/2, because that's what the sines and cosines of 30s and 60s are. They're 1/2 and √3/2. So all of these x and y's are either positive or negative 1/2s or √3/2. All right, and then, oh no. Oh. This is not easy, guys.
No.
Don't judge.
Wait, go
It's not that easy, Mackenzie. My hand won't stop.
Yeah.
This- No. Okay. All right, so let's do our 45, 45, 90. Take a square. All sides equal to 1. The diagonal of a square, and only a square, bisects each angle. So it creates two 45-degree angles. A rectangle's diagonal does not bisect the corners, does not bisect your diagonal there. Oop, that's my 90. All right, so I'm just going to take this triangle and slide them out. So I have a 1, a 90, a 45, and a 45. Little Pythagorean theorem, a squared plus b squared equals c squared. 1 plus 1 is 2. Square root it, you got √2. So now really quick, let's find our sines, cosines, and tangents of our 45, just so we have them written in a safe place if you ever want to refer back. So guys, what's the sine of a 45-degree angle? Go off either one of them. Sine would be O over H, 1 over √2. It becomes √2/2, which is the only other number labeled on those ordered pairs, √2/2. Well, guys, what's the cosine of a 45? Cosine and sine should be the same because it's the same side for A and O. So again, cosine is 1 over √2, which is √2/2. And then the tangent, since O and A will always be the same on a 45, 45, 90, it's 1 over 1, it's 1. And now, they're reciprocals, cosecant, secant, cotangent. They're just these fractions, but flipped over. So I usually have a bigger chart, but I didn't want to waste too much time today. Okay, so technically, if you can recreate this triangle, or make this chart, you really shouldn't need the unit circle. You shouldn't have to worry about having it in front of you or answering all these questions for you, because to me, it's a little bit too much of a cheat sheet. But either way, if you can draw these triangles and you know you're all students take calculus, you're going to figure out the answers to all of these questions anyway, all right? So now what I'd like to do, just to get it out of the way, your quadrantal angles, guys, they're the only angles that I do rely on the unit circle for. The ones that literally would never have fit in a right triangle, 0. How do you put 0 degrees in a triangle, right? So again, think about it like this. I use my unit circle, and it's up there. I can't have it on the screen, but I'm just going to draw a quick one. Guys, the unit circle has a radius of 1. So it's 1 to the right, so that's 1, 0. It's 1 up, so that's 0, 1. It's 1 to the left, so that's -1, 0. And then it's 1 down, so that's 0, -1. This is literally the only picture of the unit circle I'll ever draw, because I use it for my quadrantals. So guys, when I'm asked what's the sine of 0 degrees, at 0 degrees, what's the y coordinate? Because that's the sine. It's 0. So that's real easy. Because there's no triangle you could have constructed for 0 degrees. All right, what about the sine of pi over 2? What's the sine of 90 degrees? Well, guys, what's the y coordinate at 90 degrees? It's 1. The sine is 1. All right, what about the sine of pi, 180 degrees? Guys, what's the y coordinate at 180 degrees? It's 0. 3 pi over 2. 3 90-degree angles is 270. Guys, what's the sine of 3 pi over 2? What's the y coordinate at 3 pi over 2? -1. And then 2 pi, it's the same angle as 0, or it lands in the same spot. So when you go all the way around, the sine of 2 pi is the same ordered pair we already used for 0. So what's the y coordinate? 0. Okay? All right, let's do cosine of our quadrantals. What's the cosine of 0 degrees or 0 radians? Well, guys, at 0 degrees or 0 radians, what's the x coordinate? 1. Pi over 2, 90 degrees. What's the cosine of 90 degrees? What's the x coordinate at 90 degrees? 0. What is the cosine of pi? Pi radians, 180 degrees. What's the x coordinate at pi? -1. All right, 3 pi over 2, 390s, 270 degrees. The cosine, what is the x coordinate? 0. And then 2 pi brings us back to the same point we used at 0. What is the cosine of 2 pi? The x coordinate is 1. Okay, now your tangents, remember, they don't appear on the unit circle, but you build them y over x, sine over cosine. So what is the tangent of 0? So guys, at 0, put the y coordinate over the x coordinate. What's 0 over 1? 0. What's the tangent of pi over 2 radians of 90 degrees? At 90 degrees, put the y over the x. Guys, what's 1 over 0? Undefined. So technically, you can't take the tangent of a 90-degree angle. 90 degrees would not be in his function's domain. It creates an undefined output. All right, the tangent at pi. At pi radians, 180, put the y over the x, 0 over -1, 0. And then 3 pi over 2 right here, 3 90-degree angles, 270. The tangent, y over x, undefined. So 3 pi over 2 is not in the tangent function's domain. And then last 2 pi, we're all the way back here, y over x is 0. So now you can understand how the quadrantals work. They're literally based off ordered pairs that are 1s and 0s and -1s, okay? And then guys, like I said, I usually put the reciprocals, cosecant, secant, and cotangent, but all you have to do is take the cosine of that angle and flip it over that ratio to get the the secant of that angle. So let me just do this. Guys, 0 was technically 0 over 1. So what's his reciprocal going to be? If you had a tangent of 0, then the cotangent, that reciprocal, would actually end up being undefined. So the reciprocal of 0 is undefined. And then let's say you had the tangent of pi over 2 was undefined. So the cotangent of pi over 2 is the reciprocal of undefined. So now you would have 1 over 0. So what's the reciprocal of an undefined? 0. Just in case you want to write that down. Okay. So let's go, and I'm going to briefly, because guys, I don't think you're going to end up constructing the unit circle this way anyway, but just to give you the basic gist as to how it was originally created. Maybe I'll only do it with the 30, and then I'll fill it in for you guys with the other 2 angles.
Sorry, the part that you just wrote.
Yep. But guys, I remember still in pre-calc, when I was in pre-calc, that chart, we put it on an index card, and we had that index card on us at all times. All right, here we go. So 30 degrees. Think of your special right triangle, 30, 60, 90. What were our special side length relationships? It was 1 to √3 to 2, right? 30 gets the smallest side, 60 gets the next biggest, the 90 gets the biggest side. The problem is, if I want to put this triangle into the unit circle so that I have a 30-degree angle right here, the problem is this has a hypotenuse of 2. So on the unit circle, it doesn't fit. I need a radius or a hypotenuse of 1. So all they did to make my hypotenuse 1 divided by 2 Now my hypotenuse is 1, and then divide everything else by 2. And now this triangle can literally be inserted into that circle. So now a 30-degree angle will meet the circle at what point? Well, guys, if this side is root 3 over 2, what does that x-coordinate have to be? Root 3 over 2. If this side is 1/2, what does that y-coordinate have to be? 1/2. And now when you go to find your sines, cosines, and tangents, if you found the sine of 30 degrees, it's this over this. It's literally the y-coordinate on that circle. If you have the cosine of 30 degrees, it's this over this. It's literally the x-coordinate of that circle. So that's how they did it. They put the 30-degree triangle in here. Then they put the 60 in, found his point. Then they put the 45 in, found his point. And then everything else came from mere reflection and the fact that a circle has symmetry all over it. So guys, if I reflect this to the other side into quadrant 2, I still have a 30-degree reference angle that's going to fit inside a triangle. But guys, in reality, what angle are you actually at if you have a reference of 30 degrees? This is 150 degrees. So now 150 degrees passes through the point negative root 3 over 2 and 1/2 because your x-coordinate would become negative. So now you have your cosine and sine of 150 degrees. Then they reflected it into quadrant 3. So you have another reference angle of 30, but in reality, what angle are you really at when you're 30 degrees past 180? You're at 210. And 210 degrees would pass through the point. Well, if you reflect this point into there, negative root 3 over 2, and now negative 1/2. And now you have your cosine and sine of 210 degrees. And then last, 2 things you could think of it. Either you reflected this into quadrant 4, or you reflected the original into quadrant 4. And you still have a 30-degree reference angle inside your right triangle. But what angle are you really at? 30 degrees short of 360? 330 degrees. So now 330 degrees will intersect the circle at the point root 3 over 2, but negative 1/2. And if you look at your unit circle, the 4 ordered pairs for 30, 150, 210, and 330, guys, these are the ordered pairs that live on your unit circle. And they did that for every right triangle. Now they make your reference angle a 60. Throw your 60 in, shrink this down, make 60 this angle. How do the side lengths line up? And then you can label your ordered pair, and then you can reflect each triangle and each point into each quadrant. So guys, I'm gonna fill this in for you just because I know I'm running out of time. I'll fill this in for you, but that's how they constructed the right triangle. By fitting these special triangles into quadrant 1 and reflecting them into all the other quadrants, okay? Now, I have a much easier way of whipping up a unit circle from scratch than you having to draw all the triangles. So guys, if you're ever in a jam in the future, you're like, God damn it, if I had that unit circle, I'd know the answer to all these questions. Go ahead, Michael. All right. If you have to whip one up in the future, guys, it's really actually easy, and you don't even have to know what the ratios are, but they fill in amazingly quick. Michael, do you care if I come back real quick? I'm not going to erase it, but I'll just show you really quick.
Thank you.
Yep.
Sorry.
No, you're Michael, please. I go too fast. I know. I'm just trying to fit everything into a 30-minute class here. So guys, go to quadrant 1. Quadrant 1's the big one. You got to have quadrant 1 because then everything else just gets reflected. Guys, look at quadrant 1. I would draw quadrant 1, give yourself a 30, 45, 60, right? Give yourself some blank ordered pairs. What does every single ordered pair have as a denominator? 2. So give all the ordered pairs a denominator of 2. And then if you start up here at the top and count down, everything on top gets square rooted. What's the square root of 1? 1. Root 2, root 3. Just count it down. Root 1, root 2, root 3. And then from the top, you can either count up from the bottom or now count it down. Root 3, root 2, root 1. And root 1 is 1. So if you could fill it in that way, you know all of your ordered pairs as well. And then you could literally just reflect them into any other quadrant. I try to teach you to do these without needing the unit circle. But guys, I definitely have students that go, why wouldn't I use the unit circle? The answer to that question is on here. And you're right, it is. I just worry that in the future, you might not have a unit circle with you, and you might need to know the answer to these questions. All right, so again, just give everything a denominator of 2, and then it's root 1, root 2, root 3, root 1, root 2, root 3. And you've got all the ordered pairs that you need. And then everything else just gets reflected, okay? All right, so like I said, I'm not giving you any homework because I really haven't asked you any questions yet. Tomorrow, I'm going to start hitting you. I'm going to start hitting you with just, can you find the sine, cosine, tangents, cosecants, secants, cotangents of all of these special angles? And you have to know it by heart, okay? All right, so no homework tonight, so take it easy. We'll start really answering some questions tomorrow, and then homework will start tomorrow, okay? All right, if anybody has any questions, please let me know. Otherwise, guys, at home, I just got to write down your attendance really quick.